Welcome to the fourth session of this polynomial series. In this video, we will introduce and use the concept of double root to solve polynomial questions. We will go through 4 worked examples, covering the relations between polynomial zeros and its coefficients, as well as the fundamental theorem of algebra and its application in polynomials.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome back to the series of polynomial. This is the 4th session of this topic. In this session, we are going to continue to focus on solving questions using the relations between polynomial zeros and its coefficients. The first example is a cubic polynomial having an unknown constant k. It asks us to find the possible values of k given that the cubic polynomial has a double root. Since the cubic polynomial equation has a double root, we assume that alpha is the double root and the other root is beta. The expression of 4 times x minus alpha, or in parentheses squared, multiplies x minus beta is equivalent to the cubic polynomial. Let's now expand the left hand side of the equation. After collecting the like terms and equating all the corresponding coefficients to the cubic polynomial, we have 3 simultaneous equations established. The sum of 2 alpha and beta equals 0. 4 multiplies to alpha beta plus alpha squared, or in parentheses equals -7. Negative alpha squared times beta equals k. After substituting beta as -2 alpha to the second equation, we find alpha is equal to 3 over 2 or -3 over 2. Hence, we back substitute the values of alpha into the third equation and find the possible values of k that are equal to 27 or -27. Now let's look at an alternative approach for example 1. Since the cubic polynomial has a double root and we assume it is alpha, so we substitute alpha to the variable x in the cubic polynomial, and we have p alpha equals 4 alpha cubed minus 27 alpha plus k equals 0. On the other hand, we differentiate the polynomial px and then substitute alpha again to the variable of the p prime x and then set it to 0. Now we have 2 simultaneous equations established to solve the double root alpha and the unknown constant k. We start from equation 2, which is 12 alpha squared minus 27 equals 0. So we find the values of the double root alpha, which is 3 over 2 or -3 over 2. Then the calculated alpha values are back substituted into the equation 1, and the possible values of k is equal to 27 or -27. Example 2 is a cubic polynomial equation with alpha, beta, and gamma as its roots. Based on this, 3 questions are asked. The first one is to find a polynomial equation with integer coefficients given that the polynomial has the roots of alpha minus 1, beta minus 1, and gamma minus 1. The second question is to find a polynomial equation with integer coefficients whose roots are alpha squared, beta squared, and gamma squared. And the third question is asking to find the value of the sum of alpha cubed, beta cubed, and gamma cubed. Since alpha, beta, and gamma are the roots of the cubic polynomial equation, px equals the product of x minus alpha, x minus beta, and x minus gamma. As for question 1, since the three roots become alpha minus 1, beta minus 1, and gamma minus 1, the factorized form of the cubic polynomial becomes the product of x minus open bracket alpha minus 1 close bracket, x minus open bracket beta minus 1 close bracket, and x minus open bracket gamma minus 1 close bracket, which is equivalent to px plus 1. So after substituting x plus 1 as the new variable, we have the expression of x plus 1 all in parentheses cubed minus 5 times x plus 1 all in parentheses squared plus 5. After expanding and collecting the like term, px plus 1 equals x cubed minus 2x squared minus 7x plus 1. As for the second question, since the three roots are alpha squared, beta squared, and gamma squared, obviously p squared root x satisfy the original cubic polynomial equation. So we substitute square root x to the variable x in the original equation. After rearranging and simplifying, we have the cubic polynomial equation of x cubed minus 25x squared plus 50x minus 25 equals 0, which has the roots of alpha squared, beta squared, and gamma squared. As for the third question of example 2, we need a little bit more familiar with the formula of the perfect cubic. As it can be seen on the screen, the sum of alpha cubed, beta cubed, and gamma cubed is equal to the cubed sum of alpha, beta, and gamma minus 3 times the sum of alpha squared beta, alpha beta squared gamma, beta gamma squared, gamma alpha squared, and gamma squared alpha minus 6 alpha, beta, and gamma. According to the relations between cubic roots and its coefficients, we have simultaneous equations established. Based on the relations of the above, we simplify and calculate the value of the sum of alpha cubed, beta cubed, and gamma cubed, which is equal to 110. Now, let's look at an alternative approach for the question 3 of example 2. Since alpha squared, beta squared, and gamma squared are the roots of the polynomial x cubed minus 25x squared plus 50x minus 25 equals 0, and alpha, beta, and gamma are the roots of the cubic polynomials x cubed minus 5x squared plus 5. According to the relations between the polynomial roots and its coefficients, we know the sum of alpha squared, beta squared, and gamma squared equals 25. Then we substitute each of the roots, alpha, beta, and gamma, to the cubic polynomial x cubed minus 5x squared plus 5 respectively. So 3 simultaneous equations are established in this way, which relating to alpha cubed, beta cubed, and gamma cubed. After adding equation 1, equation 2, and equation 3, and since we have already learned the value of the sum of alpha squared, beta squared, and gamma squared, we can calculate the value of the sum of alpha cubed, beta cubed, and gamma cubed, which is 110. Example 3 is a cubic polynomial with alpha, beta, and gamma as its zeros. The first question is to find the value of the sum of alpha squared beta gamma, alpha beta squared gamma, and alpha beta gamma squared. The second question is to find the value of the sum of alpha squared, beta squared, and gamma squared. And the last question is to determine how many zeros of px are real. Since alpha, beta, and gamma are zeros of the cubic polynomial px, according to the relations of the cubic polynomial zeros and its coefficients. We know the sum of alpha, beta, and gamma equals -7/3. The sum of alpha, beta, beta, gamma, and gamma alpha equals 11/3. And the product of alpha, beta, and gamma equals -17. So, for the first question, we take the common factor alpha, beta, and gamma from the three terms, and we can substitute the values of -17 multiplies -7/3, which equals 119/3. As for the second question, the sum of alpha squared, beta squared, and gamma squared equals the squared sum of alpha, beta, and gamma minus 2 times the sum of alpha, beta, beta, gamma, and gamma alpha, which is equal to -17/9. There are three approaches to solve the last question. In the first one, we factorize the cubic polynomial directly by adding and subtracting the term of 2x squared, and then place all the terms in two groups. Finally, we factorize the polynomial to a linear factor of x plus 3 multiplies a quadratic factor of 3x squared minus 2x plus 17. Here we continue to work on question 3 of example 3. Since there is no real zeros in the quadratic factor of 3x squared minus 2x plus 17, because its discriminant is less than 0. So we may conclude here that the cubic polynomial has only one real zero. However, the alternative approach is to differentiate the cubic polynomial, and it becomes p prime x equals 9x squared plus 14x plus 11. Since the discriminant of this differentiated function is also less than 0, which means the cubic polynomial function px is an increasing function within its domain. So we can conclude that the cubic polynomial has only one intercept with x-axis. Therefore, px has only one real root. Another alternative is based on the result from question 2. Since the sum of alpha squared, beta squared, and gamma squared is a negative number, therefore the cubic polynomial px do not have three real roots. According to the conjugate root theorem, we may conclude that px has only one real root. Example 4 shows that alpha, beta, gamma, and delta are the four roots of the polynomial equation x to the power 4 plus px cubed plus qx squared plus rx plus s equals 0. There are four questions to follow. The first one is to find the values of the sum of alpha, beta, gamma, and delta, and the sum of alpha, beta, gamma, alpha, beta, delta, alpha, gamma, delta, and beta, gamma, delta in terms of p, q, r, and s. The second question is to show the sum of alpha squared, beta squared, gamma squared, and delta squared is equal to p squared minus 2q. The following question is to prove that the quadratic polynomial equation of x to the power 4 minus 3x cubed plus 5x squared plus 7x minus 8 equals 0 cannot have four real roots. The last question is to deduce the quadratic equation has exactly two real roots by evaluating the polynomial at the value of x equals 0 and 1. To solve these questions, we need to recall the relations between the roots of the quadratic polynomial and its coefficients we explained earlier. Here we just briefly show how these relations are established by expanding the left-hand side of the equation. After arranging and collecting the like term, we have a quadratic polynomial with coefficients expressed in terms of its roots. Here we continue with example 4. According to the relations between quadratic polynomial roots and its coefficients, as for the first question, the sum of 4 roots equals negative p, and the sum of alpha, beta, gamma, alpha, beta, delta, alpha, gamma, delta, and beta, gamma, delta equals negative q. As for the second question, the sum of alpha squared, beta squared, gamma squared, and delta squared can be expressed as the squared sum of all the roots minus 2 times the sum of alpha, beta, alpha, gamma, alpha, delta, beta, gamma, beta, delta, and gamma, delta, which result in p squared minus 2q. As for question 3, according to the relations between polynomial roots and its coefficients, and the result in question 2, we know the value of p and q here are negative 3 and 5 respectively. Hence we substitute the values of p and q and then find the sum of alpha squared, beta squared, gamma squared, and delta squared equals negative 1. Therefore, the quadratic polynomial equation cannot have 4 real roots. To deduce the quadratic polynomial equation has exactly 2 real roots, we substitute 1 into the variable of the equation and find 1 is the real root of this equation. Hence, according to the complex conjugated root theorem, the quadratic polynomial equation has exactly 2 real roots. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.